it's a pleasure to give the talk here today. It will be a rather broad overview talk because, I found it hard to judge exactly the audience I was talking to. So the title of my talk is The Recent Advances and Future Challenges in Understanding Asia's Water Tower. So what I want to do is, of course, there has been a very strong focus on glacier research. So I would like to start with a brief review about that, and then also place the importance of glaciers in a more broader hydrological context. And at the end of the talk, I also would like to just show you a few thoughts and images regarding the recent disaster in Uttarakhand, just a few slides of the recent understanding of what happened during that event. Yeah, so first a little bit about the context. We've all been working on climate change issues during the last 20 years, and I think things have changed very rapidly in how we are perceiving climate change. So already in 1912, it was quite clear that carbon dioxide was changing the climate on the globe, and you can see that here on the left side. This paper, I think this is a paper from New Zealand in 1912, where they already noted that the furnaces of the world are burning about 2 billion tons of coal each year, and that the amount of associated carbon dioxide had the potential to raise the temperature on Earth. So that was already known in 1912. And then when you look at the right side, you see an advertisement of oil company Humble and Esso, where I think this is a newspaper somewhere in the 1960s, where they proudly announced that the amount of oil that they produce every day has the capacity to melt 7 million tons of glacier. So I mean, these kind of adverts are nowadays unimaginable. So that really means that climate change is high on the political agendas and in the minds of people. And I think science has played a very critical role in this. So now let's go back a bit to the region. I think most of you are aware of the region. It's a highly diverse region, so it's very difficult to generalize anything if you talk about this region. So of course we have many different mountain ranges. So we have the Himalayas, the Tibetan Plateau, the Kunlun Shan, the Karakoram, the Pamir, the Hindu Kush, and they all have very distinctly different climates, and they also respond different to climate change. We have a huge amount of glaciers in this region, and also a lot of permafrost, and in particular the research into the impacts of permafrost on the hydrological cycle is still in its infancy, I would say, in this particular region. Then this cryosphere feeds the huge river systems that have their origin in the mountains in high mountain Asia. And if we start at the west, we have the Sir Daria and the Amu Daria, and they end up in the Aral Sea. The huge irrigation systems here that have initially started during the Soviet era. Then we have, of course, the Indus and the Ganges. The Indus is the largest continuous irrigation system in the world. And the Ganges, the Brahmaputra, the Irrawaddy, the Salween, Mekong, Yangtze, and Yellow River. So these are all huge river systems. And if you add up all the people that live in the river basins of all of those rivers, it's about 25% of the global population. So that doesn't mean that all of those people directly depend on glacier meltwater or on water from the mountains, but it does show that it is really important to understand climate change impacts in those water towers of the world. Then, of course, here you can also see the different countries, and it is also geopolitically a very complex region. There are many transboundary rivers where water is shared between countries, and there are a lot of conflicts between upstream and downstream countries regarding hydropower or water to be used for irrigation. Then let's put this also a little bit in the global context. Jürgen already mentioned it in the introduction. This is a research that we did last year, and it was funded by National Geographic. So National Geographic, together with Rolex, they had this year of the mountains. So on the one hand, they organized the highest expedition meteorological expedition to Mount Everest, where they installed a number of weather stations up to an altitude of 8,000 meters. And they funded all kinds of more small-scale research projects in the Everest region. But in parallel, they also asked us to do a global assessment of mountain regions, and indicate where mountains matter most. So what we did is we designed this water tower index, and we said, mountains are very important if there is logically abundant water resources in the mountains itself. So this can be glaciers or snow or rain or open water. But there must also be a lot of demand for that water in the downstream regions. And that water, there must be no opportunities of that water to be delivered from the downstream regions themselves. So if you have this, a high supply index, so a lot of water in the mountains in combination with a high demand that cannot be supplied in the downstream regions itself, then we consider a mountain range to be very important. So in this way, we kind of ranked all water towers based on a huge amount of globally available data sets. We ranked all water towers in the world, and you can see, I won't go into all the details here, but what you can see here is that for the different continents, on the left side, you can see the supply index. So that says something about the amount of water resources that you find in the mountains itself. And on the right, you find the demand index. So we look at different types of demands, let's say the environmental flow, the industrial water demand, the domestic water demand, and the irrigation water demand. So what you see that there is a lot of variation. So there are, for example, water towers or mountain regions that score very high in the supply index, for example, the Tibetan Plateau. So there's a lot of open water there, there's a lot of glaciers there. But there, if you look at the demand side, then you can see that the Tibetan Plateau scores, and the demand side, you can see that the Tibetan Plateau has hardly any demand because the population density there is very low. So there's no demand for it. So, but if you look, for example, at the Indus Basin, you can see it scores quite high on the supply side, but it also scores high on the demand side. So this is an example of a water tower where mountains are really, really important. So that is kind of the approach that we took in this study. So now if you look at the global picture, so here you see the final water tower index in colors. So the bluer it gets, the more important a water tower is. And what we basically concluded that all of the key water towers in the world are found in high mountain Asia. So of particular importance then are the Indus, the Amu Darya, and the Tarim, because those are all areas where you have a lot of glaciers and water resources in the high mountains. The downstream climates are arid, and there is a lot of demand for that water. And in addition, this is also a region where population is growing very rapidly in the future. So these are also the areas which are very vulnerable. So we also did this vulnerability assessment. So for all of those water towers, we looked at different indicators of vulnerability. We looked at a number of static indicators, such as, the hydropolitical tension, the governmental effectiveness, the current water stress, and then we also looked at a number of more dynamic vulnerability indicators. So how quick is the economy going to grow over the next couple of decades, and how is the climate going to change? And what we found is that the most important water towers in the world are also the most vulnerable ones. So that was the key conclusion. And high mountain Asia is really a hotspot in this regard. Yeah, so far for the broad context, then I would like to zoom in a little bit on the role of glaciers and the state of glacier research in high mountain Asia. I think the visual evidence that we have that things are changing rapidly in the Himalaya or in any mountain range in high mountain Asia is quite overwhelming. I often show this picture. This is a picture taken by George Mallory in 1921. It was never clear whether George Mallory actually was the first to summit Mount Everest, because his body was found, I think, in 1924, but about 100 meters below the summit. So people never knew whether he was on his way up or on his way down. But at least he left us this picture, and this is on the north side of Mount Everest, the Rongbuk Glacier, and this is exactly the same picture in 2007. And there's been obviously a lot of changes. This picture has been taken also by a famous climber, David Brashears. And you can see here that this glacier down-wasted about more than 100 meters, which is higher than the Dom Tower in the city of Utrecht, where I live. And there are plenty of examples of this. This is an example of the research catchment where we do a lot of research. So this is in Langtang. This is north of Kathmandu. And what you can see here is Lirung Glacier. So on the left, you see a picture taken by Tony Hagen in 1952, who was a famous explorer and one of the first to explore the Himalayas. And on the right-hand side, you see a picture taken by Jakob Steiner and with myself on the foreground. And in the distance, you see the Lirung Glacier. So you can see that now on the right-hand side, it's more like an empty bathtub, and all the ice has disappeared. While in 1952, the debris-covered glacier was still filled to the rim of the lateral moraines. So it's clear that there are a lot of changes. So this is another example, again, of Lirung Glacier. We recently found those really old pictures. So this is a picture from Erwin Schneider from the 1970s. So many of the maps in Nepal are famous Schneider maps, which are based on the photogrammetry that he did back then. So this is another example of what you can see here is that the ice that comes from the accumulation zone is still connected to the glacier tongue. And if you look now, there's a big rock band in between, and the glacier tongue actually gets no more nourishment from ice from higher up. So if we look at the region as a whole, how many glaciers are there, and how does that relate to the global picture? So this is a paper by Daniel Farinotti from 2019, published in Nature Geoscience. So it shows that there are about 95,000 glaciers in Asia, with an area about 100,000 square kilometer, and a volume of around 7,000 cubic kilometers. So that is, if you look at all the mountain glaciers in the world, that is about 4% of the total ice volume. So that may not sound large, but the big difference with many of the other regions is that this is a region which is very densely populated, of course. So a little history about the glacier research in the Himalayas. I think this really took off basically by the end of 2007. The IPCC fourth assessment report was published. And in that report, there were a number of very big errors. So the first error was that it was stated that glaciers in the Himalayas are receding faster than in any part of the world, which was not true, because we later saw that the glaciers in the Himalayas, they more or less respond at an average rate compared to all the mountain ranges in the world. And the biggest thing was that it was also stated that the likelihood of them disappearing by the year 2035 and perhaps sooner is very high if the Earth keeps warming at its current rate. And its total area will shrink from 500,000 to 100,000 square kilometers by the year 2035. Well, that was obviously a very big error, because the glaciers will not disappear by 2035, and the glacier extent was only around 100,000 square kilometers already in 2007. So what this illustrates is basically that these conclusions that made it to the IPCC report were based on gray literature, and at the time there was hardly any research available about any peer-reviewed research available about glaciers in the Himalaya or hydrology. So this error also caused the big problems for the IPCC. It almost led to the chairman who resigned, and it also caused a lot of debate. But the good thing was that it also generated a lot of funding for Himalayan research, which I think we all have benefited from in the last decade. So these were some of the news stories that happened after the publication of that IPCC report. So the real story behind it was called Glacier Gate, Glacier Estimates on Thin Ice. It also made it to Dutch newspapers and to newspapers all over the world. Yeah, so then there was also this letter published by Graham Gogley and Jeff Cargel and Georg Kaser and Kees van Veen, and they tried to track the source of this big error that was taken, and they found that it came from grey literature published in a WWF report, and yeah, so that actually shows how important the role is that we have as scientists, and to make sure that whatever we do is reproducible and published in good journals. Luckily, since then, the amount of knowledge and peer-reviewed studies on glaciers has increased tremendously, and it's unimaginable what we know now relative to about 10 or 15 years ago. So let's first look at the mass balances. So you probably all know what a glacier mass balance is. It's the difference between the accumulation and the ablation, and it tells you in what state a glacier is. So this is kind of the latest state of the art. It's a study by David Sheen, published in 2020 in Frontiers of Earth Science. And he combined a huge amount of digital elevation DMs based on worldview, satellite imagery combined with Aster imagery. And based on that, he quite accurately derived mass balances. And you see that here, aggregated in cells of 55 by 55 hexagonal cells. And you can see a very clear pattern that everywhere along the southern arc, we see strong negative mass balances in the order of 40 centimeters of water equivalent per year. And we also see a very interesting place around the Karakoram and the western Kunlun Shan, where glaciers seem to be gaining mass, or at least are stable. So that's also very interesting, and I'll come back to that later in the talk. Another benchmark study in this respect is the study by Amaury de Hek, published in 2017. And what he did, he tried to analyze the flow velocity of glaciers. And that's also very interesting because the patterns match very well with the mass balance patterns. So what you see that all along the Himalayan arc, on the southern part, you see that glaciers are slowing down between 2000 and 2017. But again, in that area around the Karakoram and the western Kunlun Shan, the glaciers are accelerating. So that is very clear that those signals are matching. So, but this DM, all these kind of studies are based on DMs and DM differencing, and there have been several benchmark studies in this field, and I've tried to summarize them here. So this all started by the study with Andy Cape, who combined ISAT with SRTM. And then there was Alex Gardner, Julie Gardell, Andy Cape did an update of his previous study. Then Fanny Brun, who based it all on Aster DEMs. And then the last study of David Sheen that I showed. So what you can see is that there's quite the numbers in red are the average mass balance of whole high mountain Asia. And there you can even, for the entire region, you can see there's still quite a lot of variation between the different studies. And this is, there are different reasons for this variation. A key problem was, of course, for those studies that have used SRTM, is that's basically a radar signal, and the penetration of the radar into the ice is quite uncertain. So that is one reason why there seems to be a systematic error for those studies that have used the SRTM as a reference DEM. But you can see that slowly we are converging, and if we look now, we are about, for the whole high mountain Asia, we have an average mass loss annually of about 0.2 meters of water equivalent per year. Then a lot of people and a lot of studies have also been devoted to understanding this Karakoram anomaly, or that one area that I just showed where the glaciers are stable or seem to be gaining in mass. So what we did last year, we did a kind of a review study of what are now the manifestations and mechanisms that cause this anomalous glacier behavior in this region. But what's interesting that Ken Hewitt was one of the first who already detected that glaciers are behaving anomalously in the Karakoram already in 2005. He noted this. So what we did in the review is, we looked at different kinds of reasons what could potentially lead to this anomalous glacier evolution. So on the one hand, there are studies that say, well, it's all it is related to climate change and changes in large-scale atmospheric forcing. So the monsoon could be weakening, or the position of the westerly jet can shift to the north, which draws colder air into the Karakoram, which in the summer, which could be a reason. We have been working ourselves in our group a lot on the role of increased irrigation in the region. So I'll say a little bit more about that and how that perturbs the regional climate, and as a result causes extra snowfall in the mountains. Then the Karakoram also has very specific glacier properties. So many of the glaciers there are fed by avalanches with very steep accumulation areas and very long and elongated glacier tongues, which is distinctly different from what we find in the for example in the Himalayan arc. And the climate by itself is already different. So in the Himalayas, it's a monsoon climate. So 80% of the precipitation falls between June and August. While when you go to the Karakoram and the Tian Shan, there is also a very strong precipitation contribution during winter. So all of these processes together shape how the glaciers are responding and have been responding in the past. Then a little bit about this irrigation hypothesis that we have been working on. This is work by Remco de Kok, who was a postdoc in my group. So our hypothesis was that, particularly in the Tarim Basin, but also in the Indus and in the southern part, there has been very strong increases in irrigation and irrigated areas. So in the Tarim, there has been a lot of groundwater pumping in the desert, and a lot of green areas have popped up there. So obviously all that water that comes from the groundwater is evaporated, gets into the atmosphere, and changes the regional climate. So our hypothesis was that because of the fact that you get that additional moisture in the atmosphere, that can potentially lead to more snowfall and more clouds in the mountains. So more snowfall, of course, adds snow and ice to the glaciers, and more clouds protects, causes less incoming shortwave radiation. So that's a double effect, which would favor glacier mass growth. So here you can see an example of the greening pattern in high mountain Asia. So these are NDVI trends between 2000 and 2010. So you can very clearly see, particularly in the Tarim Basin, that there's a lot of irrigation areas there. And we also used a moisture tracking model to assess if that extra moisture in the atmosphere will also actually end up in the mountains. So then we did some model experiments with a weather model, a WRF weather model, and what we did is we looked at the role of irrigation, and of course that has a temperature effect, but also a precipitation effect. And basically the main conclusion is if you include both the temperature and precipitation effect of additional irrigation, then the simulated mass balance, so we coupled this to a glacier model, the simulated mass balances, they match quite well with the observed pattern. So you do indeed see that in the Karakoram and the Western Kunlun Shan, there is an increase in mass balance. Yeah, so this is more the very large scale patterns in glacier response, but I also came to realize more and more in the last 10 years that if you really want to understand how the system works, you also have to look at the really small scale. And what we did a lot of research also with drones and UAVs, and in particularly we looked at debris covered glaciers because they are a particular feature of Himalayan glaciers. And many of the tongues are covered in a thick layer of debris. You can see a picture here. The surface is very variable. So we have ice cliffs, lakes, there is this debris on top of the glacier. So all of those things, of course, they have a big influence on how fast the glaciers melt. So according to the theory, a very thin layer of debris, and you see that on the plot on the bottom left, very thin layer of debris actually accelerates the melt because it darkens the surface. So this is an albedo effect. It captures more shortwave radiation and it increases the melt. But very quickly, when debris layer gets more than 10 centimeters or a few centimeters, it starts to insulate the ice from melting. So we tried to investigate that with drones. So we did a lot every half year. We did drone flights over a number of benchmark glaciers, and we tried to, with those drones, we can derive very detailed elevation models and a resolution of 20 centimeters or something. And then when you subtract those elevation models between different time steps, then you can get a really detailed insight in the spatial melt patterns. So this is more the large scale. What's the difference between the debris covered and the clean ice glaciers? And what is interesting to note is that even though, according to the theory, the debris covered glaciers are supposed to melt at a less fast than the clean ice glaciers, and what you can see here is that they are even melting faster, and particularly during 2000 and 2016. So that is something that has been puzzling also quite some scientists. Why are those debris covered glaciers melting as fast or maybe even faster than their clean ice counterparts? Of course, there are differences in elevations and you have to be careful in comparing it, but this was quite a clear signal. So what we saw with the drone is, this is an example of that very detailed elevation models that you can generate. You can really see all the details. This is a trend in the melt over a period of, we started in 2013 and the last one was in 2018. So this is a melt pattern of the Lerum Glacier. So that's the same picture that I showed in the beginning, these very old pictures. So you can see that this pattern of melt is very variable. So we see in general it's red. So this means that the tongue is losing mass, but you can also see this really big hotspots and even some areas where we have a positive surface elevation change. So what we found is that, those hotspots of melt, those dark red places, sometimes the melt there is a factor 10 times higher as the average. So on average, it's about, the glacier loses about 85 centimeters per year in thickness. But in some of those hotspots, it can be a couple of meters or even up to 10 meters per year. So we found that those are areas where you have those ice cliffs or those supraglacial ponds. So they are really accelerators of melt that we find. We also, this is the terminus of the glacier where we have a lot of exposed ice. So it's quite interesting to see this is all the different time steps that we have. So we can really reconstruct how the whole terminus has developed and withdrawn over the last 6 years between 2013 and 2018. So you can see that it withdrew already in this case about 250 meters in such a short period. So we identified, that those glacial lakes and ice cliffs are important, but then we went even a step further because, of course, if you want to understand why there is so much more melt at those ice cliffs or lakes, you have to understand the energy balance in detail for those places. So it's a PhD student in my group, and she worked with an LES model, and she modeled the turbulent fluxes in a very high level of detail. You can see here, this is just a single ice cliff where she has, and you can see here the potential temperature, and you see how the heat is transported and how this cold ice cliff is being influenced also by eddies that come from the opposite side. And on the right-hand side, you see also a spatial pattern of the net energy over the entire glacier. So, when you go, if you really want to understand the fundamental processes, you have to also go to these kinds of small scales. So I think that's also so interesting about this kind of research. You want to understand the general patterns, but then, when you zoom in and you zoom in and you zoom in, you find many interesting things at a very small scale as well. So the last thing about glaciers, which is really important, I think, is that's also a lot of recent work, is a lot of proglacial lakes are developing in the Himalayas at the end of glacier tongues. And this is a picture by Scott Watson. I think it's the Tsorolpa lake, which is a famous lake in Nepal, and this is the Imja lake. So what you can see is that there's a lot of calving happening at the terminus of this kind of glaciers. And what you also see is that glaciers which end up in a lake, they are retreating much faster than land terminating glaciers. So it's clear that this calving plays a role, but the exact mechanisms are not really clear. So this is work by Owen King and Tobias Bolch, and they looked at the difference between lake terminating glaciers and land terminating glaciers for the whole region. And so you see in the orange lines are the lake terminating glaciers, and the black line is the green dotted line is the land terminating glaciers. So you see that everywhere the lake terminating glaciers are losing mass much faster than the land terminating glaciers. So this is another key process in understanding the glacier response. Now let's take a step back again to the whole region. What is going to happen in the future? So there are quite some studies have been published now. So this is a study also that we did in our group that was published in Nature in 2017, where we try to look at what does the Paris Agreement of 2015, where all countries agreed to try and limit the global warming to 1.5 degrees. What does that imply for the glaciers in Asia? Because that 1.5 degree is quite an arbitrary threshold. So the first thing that we showed is if the global warming is 1.5 degrees, that means actually that in high mountain Asia, the average warming is about 2.1 degrees. So that means that's a process called elevation dependent warming. So it shows that, the high mountain Asia is even more sensitive to changes. And that elevation dependent warming is also consistent in all RCPs. So if you go to more extreme scenarios, you still see that the warming in the mountains is stronger than the global average. Then just some quick results. So what does that mean? Let's say if we are able to constrain the global warming to 1.5 degrees, that means we will still lose about 36% of the total glacier mass by the end of the century. That is what our models showed us. And if we go to more realistic scenarios, so RCP 4.5 or 6.0, it means that we will lose about 50% of the total ice volume by the end of the century. So you can see this is quite a different conclusion than the IPCC report of 2007, which said that most of the glaciers would have been gone by 2035. But still, it's a pretty dramatic message. Then, as I said in the beginning, you cannot generalize. So here is also the spatial patterns in change that we modeled. So in the colors, you see the temperature change. So that's the pre-industrial minus the end of the century. So what it does show is that the Pamir, the Hindu Kush, and the Karakoram, they show the strongest warming. But there are other, that's about 2.3 degrees. And there are other regions where the warming is a bit less strong. And then the pie charts, they show the reduction in area under the 1.5 degree scenario. So, and then you have three different time slices, 2040, 2070, and 2100. And you can see how the area is going to retreat in the future. There you also see quite some differences between the regions. So for example, in the Kilian Shan or Tibetan Plateau or Eastern Himalayas, you see quite a strong reduction in area. But if you look in the Karakoram, for example, even though the warming there is the strongest, you see that the area reduction is relatively small. There's still 75% of the area left by the end of the century. And that also has to do with the glacier properties. So the glaciers in the Karakoram are huge. Glacier tongues can be 30 or 40 kilometers long, and with 500 to 1,000 meters of thick ice. So that just takes a huge amount of time to respond to climate change. And if you have smaller glaciers, the response time is much shorter. So that's basically what you see here. Well, I won't go into detail of this, but these are the total projected ice volumes for all the different mountain regions that we projected. So in the bottom right, you can see the differences. That's the total, so for the entire region. And yeah, you can see the black dotted line is the 1.5 degree projection. And then in colors, you see the projections of the different RCPs. So there's really a big difference between whether we are able to keep the global warming to 1.5 degree or whether we are going to much more. That has a very big impact on the total ice volumes. Yeah, so far quite an overview of the glacier research in the region, but let's go now to the hydrology. This was already a bit mentioned in the beginning. So this is a paper we did already more than 20 years ago now, that was published in Science, and it was also after that IPCC report. We actually thought, well, how important are the glaciers in the, let's say, in the greater scheme of things? And the interesting thing was that there's a lot of variation in how important the glaciers are. If you look at the western part, so what I show on the right is the normalized melt index, which is a measure of how important meltwater is in the overall hydrology. So the main conclusion already then was, in the Indus, glacier and snow melt are really important. But if you go further to the east, the glaciers are not really important, at least at the river basin scale, because there's so much monsoon rains which occur simultaneously with the melt season, that the contribution of glacier melt to the overall river flow is relatively small. So we also must keep that perspective. So even though there has been a huge focus on glacier research, there are other parts of the hydrological cycle which are very critical as well. So then there was a follow-up study by Arthur Lutz in 2014, where we really tried to quantify the spatial variation in meltwater contribution. So this basically tells us the same story. In the three maps, you see the different contributions of glacial melt, snow melt, and rainfall runoff. And you can see if you are very far in the west, high in the mountains, in the Karakoram, glacier melt is very important. But if you look all along the Himalayan arc, you can see that it's really the rain contribution that drives the river flow in the rivers. So this is a very recent review that came out in Nature Reviews by Yongni et al. And that was also partly based on our results, and they looked also at the future runoff. So in the top three plots you see for the upper Indus Basin, the upper Ganges Basin, and the upper Brahmaputra Basin, you see the different runoff projections. So the gray bar is the total runoff under the current climate. And then the PTR is the projected total runoff. You see the different colors. So green is the base flow, pink is the rain runoff, yellow is the snow melt, and blue is the glacial melt. So what you actually see is that for the future, it looks quite boring. There's not, in terms of average water availability, not much is going to change, and it's getting a little bit wetter. And that is a combination of an increase in glacial melt and an increase in precipitation that is projected by most climate models. So in terms of general water availability, we kind of concluded we don't have much to worry about over the next decades. There will be plenty of water, and most climate models predict a stronger monsoon. So on average, the amount of water that comes down from the mountains will more or less stay the same or increase a little bit. So in the bottom, you see also the year of glacier runoff peak. So this is the year when the glacier melt contribution is largest. So that's also quite variable, but you see it will take quite a lot of decades for most regions until we reach that point. This is a bit similar. This is a time series of the glacial runoff change that we find. So you see that stays fairly constant for a long time. And there are in the bottom those are some results of the Langtang catchment of the different contributions and how they change. So what you can see between 2000 and 2075 for this very small scale study is that, you know, the general pattern remains the same. The glacial melt contribution is reducing in summer, but the extra rainfall is compensating that. Does that mean that there is no problem, or we don't have to make adaptations? I don't think so. I think there are two critical things that may change in the future. One is the seasonal shifts. One example of that I want to illustrate with this study of the Upper Indus Basin. So we did a detailed modeling study here, and in those blue bars at the right side, you see the change in projected runoff. So that's the total runoff, including all contributions. And we've done that for several points where we also had runoff measurements in the basin. So you see those points on the right. So what you generally see is that in general, it gets wetter. But in particularly in the second half of the century, 2071, 2100, you see a kind of attenuation of the river flow. So during the monsoon season, let's say the runoff gets less, and in the shoulder season, there's much more river flow. So the snow melt comes earlier. There's less rain predicted in the summer season. So those kinds of shifts we have to adapt to, because of course there are big agricultural areas downstream that depend on water in specific months. The other challenge is basically the increase in hydrological extremes. So if glaciers are retreating and perennial snowfields are reducing, there's a lot, the whole hydrological system changes. So we get a lot more of exposed rock, and the buffering role of the cryosphere disappears. So the system basically accelerates, and a drop of rain that falls ends up in the river faster than it used to be when it turned into snow, ice, became a glacier, and slowly melted in periods when it was warm and there was no rain. So this is a study by René Wijngaard, also for the Indus, Ganges, and Brahmaputra, where he did a first-order assessment of the potential changes in the peak runoff. So what you see here is for the two climate scenarios, the change in 1 to 50 years extreme runoff. And you can see basically, in particularly along the Himalayan arc, that you get a very strong increase in this peak flow. And of course, we all know, and this whole project is about that, peak flows and flooding cause millions of damages every year. So the final part, what we are also increasingly more interested in. So on the one hand, we have, of course, the physical changes in the system and climate change that changes, the timing of water availability, and that changes the peak flow. But maybe even a bigger bigger driver of stress to the system can also be the socioeconomic developments. So we started with this already a few years back, and we coupled our physical models of the hydrological models from the mountains. We coupled that to agricultural and water demand models downstream. And what we try to quantify is really how much of the irrigated agriculture really depends on snow and glacial meltwater. So this is one result from that paper that was published in 2019. So in the rivers are shown in colors, and you can see there the mean annual contribution of snow and glacial melt to discharge. So that basically follows quite well of what I showed earlier. So in the western part, you see that meltwater has a very important contribution, and in the eastern part it's much less. And then in green you can see how much of the irrigation water supply actually comes from snow and glacial melt. So we track that water, and we combine that with an advanced agricultural model downstream to really try to attribute that. And then again, you see that in particularly the Indus is really a hotspot where a lot of the irrigation water comes directly from meltwater. And that meltwater is stored in a number of major reservoirs like Tarbela and Mangala dams, and they store that water and they supply that huge irrigation system downstream. So if you look at the future, I think this is again for the three different basins. What we are going to see is a very steep population growth, which is projected for all three basins. And we also see a very strong economic growth. So people get richer and diets are changing. People eat more calories per person. A lot more energy is required. A lot more cropland is required. So all of this together, I think, will cause an exponential growth in the water demand in the future. And that growth in water demand, I think, is even a stronger impact than the climate changes that we are seeing. So this is also recent work about where we try to estimate that water demand by making detailed population projections. We looked at different scenarios, where we looked at a scenario that focused purely on urbanization, scenario that looked more from highland to lowland migration, and a scenario where we looked at the south to north migration on the plains to avoid increasing heat stress. So in all those cases, we see a very rapid increase in population and an associated demand in water. So basically the takeaway points from my talk is, I think we have had a lot of focus on glacier research, but we should also acknowledge that the full picture is much more complicated. That we really have a lot of key unknowns in the mountain water cycle. And of course, everything is being driven by precipitation, but still we know very little about precipitation at high altitude. There are hardly any stations that measure precipitation or snowfall above 3,000 or 4,000 meters in the Himalaya or Karakoram. And of course, that drives everything. So a lot of strong conclusions are drawn, but we still have a very large uncertainty about the key hydrological input in the system, which is precipitation. Then another knowledge gap, I think, are the snow dynamics. We know quite little about snow accumulation, snow sublimation, which can be an important loss of snowfall, the wind redistribution, and the snow hydrology. So the models that are being used, in particularly the large scale ones, they are quite simplistic in terms of how they deal with those snow dynamics. A third component is, I think, is evapotranspiration and greening. So we have a really strong focus on the cryosphere at high altitude, or we look at the downstream plains. But a lot is happening in between the high mountain peaks above 6,000 meters and the plains at close to sea level. So I think in the middle mountains we see there's a lot of evapotranspiration and greening. And that also has, of course, a huge potential to change the whole water cycle in the mountains. But very little research is being done into that field. And finally, I think, Chris Anderman is, of course, one of the key persons who's working on this. The role of groundwater is also quite important, in mountain hydrology. And there's only a limited amount of research being done into that field. So more at a larger scale, I think the key challenges that we have to deal with for the future is to understand and predict extremes and natural hazards. That's very complicated because, of course, then you also need to have accurate forcing, and you need to understand, it's all very probabilistic, and which events lead to which natural hazard and what impact that hazard has is very complex to quantify systematically, in particularly for larger regions. And the last point is that I think the key is to acknowledge also that the increase in water demand is going to be a major challenge for the future, and we need to adapt to that. So that was basically my talk. And then if I still have the time, I would like to give you some thoughts on the Uttarakhand disaster. I was that I followed also very closely, and I think it's also a good example of how we, with collaborative science and with remote sensing, we can very quickly make some first assessments and try to understand what has happened very fast after such an event has happened. So as you probably all know, on 7 February, at 10:30 in the morning, a major debris flow was witnessed in close to Chamoli, and it destroyed for a large part the Rishiganga hydropower plant, which was still under construction. Yeah, a lot of people immediately started to try and understand what happened. There was a lot of reports in the media. First, there was this story about a glacier burst, which I think it's not really a scientific term. And there was stories of glacier ice that hit the hydropower plant directly. And then there was other reports of glacier lakes somewhere upstream in the Nanda Devi Basin that caused a flood and that caused the event. And yet 100 people were missing. There was a lot of damage. So the big question is this now, can you attribute such an event to climate change, or is it just bad luck, and is it something that can just happen in such extreme environments? So what happened is that a few hours after the event, there was already a satellite image available. So this is a satellite image from planet.com. So they have this whole constellation of DAF satellites. So those are tiny satellites. And with that constellation, they can observe, let's say, almost every place on Earth with a resolution of, I think, 3 meters, depending on which type of satellite it is. Every few days. So by coincidence, there was an image right after the event. And what you saw is here that there was an area about 20 kilometers away. So the hydropower plant is that blue spot in the map, and the red area is the source area. So what was found out quite quickly is that it was a catastrophic slope failure, and that a huge amount of rock mixed with ice came down, and that this transitions into a debris flow on its way down, and that was the cause of the destructive debris flow. So here you can see some different images. So this is 6 February versus 9 February. So you can see that on the right hand side you see that whole scar, and it's a huge amount. I think I have a better one here. So yeah, it's a huge, it's quite large. It's about 500 meters in width and about 1 kilometer in length, and I think over 100 meter in depth. So that is a huge amount of rock and ice that came down. And the source area was about 5,500 meters, and it came down to 3,800 meters. So on the right-hand side, you see a kind of 3D visualization also with that planet image overlaid. And then you could see that. But here are again some different DEMs between May 2015 and 2021. This is made by Etienne Berthier and Simon Gascoigne using Pleiades imagery. So you can really see that, it is on the right-hand side, you can see in that red triangle is basically the volume that was released. So it's really 150 meters thick and about 1 kilometer long. That whole wedge came down. So some initial energy calculations were also made by my colleague Jakob Steiner. So if you assume the impact energy, you calculated that the volume of ice and rock that came down was about 5.2 times 10 to the power of 10 kilograms of rock and ice. And if you drop that over 1,600 meters of elevation, you get a huge amount of energy, which is equal to 10 times the bomb on Hiroshima. So you can imagine the amount of energy and destruction that has caused. The big question that many people had, well, then what was the source of all that water that came down? Because if this was just rock and ice, but it can also be that, there's a lot of ice remnants on the valley floor, and this energy can actually liquefy what it finds on its way. So that is now the current hypothesis. But of course, this is very, very preliminary analysis. I think it's a great example of what remote sensing and high resolution remote sensing can now do in terms of identification of natural hazards, and that has a lot of potential. And I think 10 years ago, this would not have been possible at all. Within a few days, people reconstructed in a very collaborative way what had happened. Thank you very much.